A conventional turbocharger uses the engine's exhaust gases to power a turbine, which drives a compressor to force more air into the engine. This allows the engine to produce more power without increasing its size. When you have the right combination of air and fuel, it will burn efficiently and the engine will produce maximum power. Conventional turbos have come a long way since they were first developed in the 1890s. Thanks to advancements like twin scroll and variable geometry turbos, manufacturers have been able to increase the responsiveness and power outputs of these turbines considerably. However, the fact remains that it still takes time for the engine to produce enough exhaust gas velocity to spin a turbo. So despite all advancements, turbo lag has not been completely eliminated. And while mechanically driven superchargers do offer quicker response times, they also consume up to 10 kilowatts for every PSI of boost, draining vital engine horsepower. But now, with 48-volt electrical systems becoming increasingly common, manufacturers have developed a new type of turbocharging technology which promises to further reduce lag and boost engine efficiency. The basic premise of electric turbocharging is to deliver boosts much faster by using electric power to do one of these three things. Supply extra air to the exhaust-driven turbos at low speeds, provide extra boost to the engine directly, or physically increase the turbine speed with e-assistance. At present, almost all road-going versions of this technology take the first two approaches, using something called an electric compressor design. We'll cover that in more detail shortly. What's important to know first, however, is that electric turbos of any kind are major power consumers, draining around 7 kilowatts at peak current draw. Using a conventional 12-volt system, this would equate to a massive 583 amps of current draw, which would flatten the battery extremely fast. With a 48-volt system, however, this is reduced by 75% to around 145 amps at peak current draw. With that cleared up, let's now dive deeper into electric compressor technology and understand how it works. In simple terms, an electric compressor turbo is an electronically powered compressor that does not rely on exhaust gas at all to spin it up. Instead, a high-speed electric motor attached to the compressor wheel spins up to 70,000 RPM in less than 250 milliseconds. There are several different variations on the market today. Let's have a look at a common application using an e-compressor. At idle speed, the conventional exhaust-driven turbocharger is used. The intake air charge is routed like a conventional turbocharger with the bypass valve in the fully open position. As throttle is applied and engine RPM increases, a transition effect takes place. On initial acceleration, as engine revs increase to above idle speed, the bypass valve begins to close, directing some charge air through the e-compressor. Essentially, at this point the e-compressor and the turbocharger are briefly running in parallel. Somewhere between 1100 RPM and 1500 RPM, the bypass valve fully closes, diverting the conventional turbocharged air in series through the e-compressor only. The effect of this is to overcome traditional turbo lag at low RPM. Over approximately 1500 RPM to 1800 RPM, the traditional exhaust-driven turbocharger is spinning at higher RPM and on boost, negating the need for the e-compressor. As a result, the bypass valve opens fully again and the e-compressor electronically switches off. The result is that engine torque at low RPM is maximised, allowing OEMs to fit larger conventional turbochargers that boost power at higher engine speeds without compromising throttle response lower down in the rev range. Another major benefit of the electric compressor is packaging. It can be located away from high heat sources in the engine bay, taking away a hot turbine that would otherwise be located close to the intake tract. This increases engine efficiency by not heating up the intake charge. It also means the electric compressor can be placed closer to the intake manifold, reducing intake ducting. Now that we've covered electric compressor turbos, let's take a look at another form of electric turbocharging. Unlike electric compressors, electric assist turbochargers mate a traditional exhaust turbo with an electric motor, which is mounted directly on the shaft between the compressor and the turbine. They look surprisingly like a traditional turbocharger, with a slightly larger centre housing that houses a brushless, permanent magnet motor. A Hall effect sensor is used internally within the electric motor to monitor turbo speed for feedback to the engine management system. To minimise heat transfer along the compressor and turbine shaft to the electric motor, airflow through the centre housing is controlled with the addition of an air pump forcing air through the hollow shaft via a nozzle and out the other end, cooling the electric motor. More advanced OEM prototypes of this technology now also use pressurised bleed-off air from the compressor to provide airflow which cools the main shaft. Using electricity to accelerate the shaft during times of high demand also adds more control to the compressor wheel, allowing boost to be finely adjusted to suit different engine and driving conditions. Finally, E-Assist turbos have the ability to deploy the electric motor in the turbo as a generator, harnessing energy when the turbo is spooling down. Rather than losing excess exhaust gas to the wastegate, the E-Assist turbo converts this loss into additional charge for the battery, improving efficiency. At this stage, electrically assisted turbochargers are still an emerging science, and the first OEMs are yet to throw their hats into the ring and adopt the technology. However, that doesn't mean the technology isn't being used in the automotive space already. Formula One introduced the E-Assist turbos as part of the Kinetic Energy Recovery System known as KERS for the 2009 season, which uses the MGU-K for kinetic energy recovery from braking. Current is fed into an electric motor on the front of the engine from a turbo motor generator unit or an MGU-H. This provides up to 80% extra horsepower for up to 6.7 seconds per lap. KERS is designed to harvest a portion of waste exhaust gas energy from the turbo and braking system and redeploy it into the car as extra horsepower, providing a performance advantage to its driver. The MGU-H captures waste thermal energy dispelled from the turbo exhaust to generate electrical energy in conjunction with the MGU-K unit, used later to assist powering the electric turbocharger and electric engine assist motor. Drivers use the extra boost via the electric assisted turbo out of slow corners to help reach top speed and for passing on the main straight, by spinning the turbocharger faster when exhaust gas energy is low. While electric assist turbos are not yet on our roads, several production vehicles are already using electric compressor technology. We can expect to see many more OEMs adopt the technology as they seek to meet more stringent emission regulations. Understanding electric turbocharger technology is therefore essential for any technician who wants to be confident in diagnosing and repairing tomorrow's forced induction systems. Thanks for watching, and remember, keep training.